Hi, my name is Barry Olney from In-Circuit Design. This is a quick demonstration of the new features of the 2016 release of the PowerStack suite. One of the main features we've incorporated in this year's release is an EMI plot for the PDN planner, and I'll demonstrate that now. First of all, we'll start off with an standard 8-layer PCB that we have in the stack-up planner, and we'll open up the PDN planner. And I'll load a standard DDR2 PDN. Now, years ago, we were told that if we added 100 nanofarad capacitor and 100 picofarad capacitor every power pin on the main chips, it would be sufficient to handle the PDN. We also throw in a few tantalum capacitors, which drop the lower end of the impedance down. And you can see that if we look at the 100 picofarad capacitor in particular, its resonant frequency is around 600 megahertz, and that happens to be our clock frequency, 600 megahertz. So this is not too bad a PDN actually, considering it's very, very low impedance at the fundamental clock frequency of 600 megahertz, and it's low from 400 megahertz up to around a gigahertz. We do have a peak in the PDN around 330 megahertz, but that's way below our 600 megahertz fundamental frequency. So looking at it from a PDN point of view, it doesn't look too bad. So let's look at the new feature of the EMI plot. So we'll open up the EMI plot. Now this is a radiated or predicted radiated emissions plot of the PDN. The emission looks fairly bad up here in the high end, but this really only appears when the planes are excited by a signal. So if our clock frequency or one of our harmonics of the clock frequency excites the power plane pair, then it will start to resonate and build up a standing wave at that particular frequency. And then we have this dreaded rogue wave effect where you have a slow frequency beats with a high frequency resonance of the plane and creates a peak in the PDN. So what we want to try and do is avoid this at all costs. So let's zoom in on this a little bit, and we'll just change the minimum frequency to 100 megs, so we expand the scale out, and it goes up to 100 gigahertz, you can see. Now here, first of all, we have our radiation at 300 megahertz, which is 38 dB, and you can see here I have a FCC Class B EMC limit. So the EMC limit below 1 gigahertz is 46 dB for the FCC Class B, and it goes up at 1 gigahertz to 54 dB. Although the EMC regulations don't really extend past 1 gigahertz at this stage, we can expect them to go up in frequency as time goes on. So this is the FCC Class B. We can also select Class A, which is a lot more forgiving, and it has a higher maximum radiation of 60 dB above 1 gigahertz. And we also have the CISPR Class A, Class B, which they use in Europe and Australia, and the VCCI, which is used in Japan and some countries in Asia. So we'll concentrate on the FCC Class B to start with. So we have a peak, as I mentioned, at around 300 megahertz here, which is not really a problem because it's well below our fundamental frequency. Now here's our fundamental frequency of the DDR2 RAM. It's around 600 megahertz, and you can see here the radiation is very, very low at that frequency. So what we need to do is look at the odd harmonics of the fundamental frequency. If you do a Fourier transform on a square wave, if the Mach to space ratio is roughly even, then the even harmonics are cancelled out, leaving you only with the odd harmonics. So the ones of importance are the third harmonic. So you can see here at the third harmonic the radiation is quite low. The fifth harmonic, and that is a shocker, and you can see it. So it's just over the FCC Class B limit. If we now look at the seventh harmonic, you'll see that this is very, very close to this spike here in the PDN also. And so we really need to make sure that these harmonics aren't over the limit. And we can go up to, say, the 9th and the 11th harmonic. The 11th harmonic is 6.6 gigahertz in this case, and this peak here is at 6.9, which is fairly close. So really, these are the three peaks that we need to get rid of. Alright, so how do we go about doing this? First of all, I'll change this to the 8-layer stack-up, which I should have done, and it hasn't varied it much. So we'll look at our 8-layer stack up and see what we can do from a stack up point of view. We have our two planes in the center of the board, and in this case we have the core, which is 14 mil thick, and that's quite large, and that doesn't give us a lot of natural coupling between the two planes. So let's reduce this to 4 mil to start with. So we've now got a finer dielectric between these two planes, and that should give us more capacitance. So we'll go back here to the EMI plot and we'll read that 8-layer stack up back in. And you can see just by dropping or by increasing the planar capacitance in that core material, we've reduced the PDN on those three. So this at this stage would be acceptable at below the class FCC Class B limit. But let's see what else we could do. We could go back here and we could change this material, edit the dielectric material in its core, and we could put in, for example, a Sanmina ZBC 1000 material, which adds planar capacitance. Now, the new dielectric materials library, because we have so many materials now, we have 23,280 materials up to 100 gigahertz. So in order to speed up the response of the library, because we have so many materials, we have a new manufacturer's selection. So here we can select any manufacturer we like from the list here. And what I'll do is I'll look at the Sanmina materials. And the ZBC 1000 has a 1 mil thick dielectric. And this will in fact give us 0.9 nanofarad per square inch of planar capacitance. So we'll go back to the PDN planar and we'll reread in this 8-layer stack up. And again, you can see that the peaks have been reduced. So all the time when you change that planar capacitance, it reduces your PDN and stops the emissions. We can go even further, and if we go back to the stack up planar again and we edit this again and we use, say for instance, a free M material this time, an embedded capacitance material, they go down to 0.24 mil. So we'll read this in, and that gives us 20 nanofarad per square inch, which is a lot better than the Sanmina. So again, we'll read in this 8-layer, and you can see how it's been reduced dramatically. So that is one good way of doing it. We could even change the plane area. So if we reduce the plane area from, say, 2 square inches to 1.5 square inches, this will also dramatically improve our EMI. So this is really a perfect PDN because it has very, very low emissions with that planar capacitance in there. But, you know, that's all very good, but it's added cost to the cost of your print circuit board. So let's go back to our standard 8-layer board, and we'll see what we can do other than that. So we'll read back in our 8-layer board, our standard 8-layer board. And you can see already by reducing the size of the area of the plane pair, we have reduced the radiation. So we can knock this down quite a bit. The smaller area, the less resonance you have, and it moves the resonance up in frequency. So even just by changing the area of the plane, of the DDR to 1.8 volt plane, you can reduce the radiated emission. So it's really a combination of the stack up, adding planar capacitance as much as possible, and reducing the area of the planes, or shifting the resonance of the planes so that we're not on the harmonic frequencies of the fundamental. So going back here, a good compromise for this would be, say, to have a 4 mil core, which is quite inexpensive and readily available, in the center of our stack up, and that will give us a very good response. So with a 1 inch square plane area, which is doable on a DDR2 design on our 1.8 volt rail, we have very low emissions. So that's really for a bad PDN when we're just using a standard 100 nanofarad and 100 picofarad capacitor with a tantalum. So let's look at a more optimized DDR2 design. Now this one is a 14-layer board, and I'll just swap this over to pull in our standard 14-layer stack up. So So we'll select the 14 layer stack up here, and we'll go back here and you can see that our 14 layer has planar capacitance again in the center of the board here. So this is a good stack up for DDR design. And looking at this, the PDN is pretty well below the target impedance up to the target frequency, in this case of 400 gigs, the fundamental frequency. So let's look at the PDN plot of this particular one, or the EMI plot. And you can see that it's well below the FCC class B limit in this case. So our resonances, our harmonics, there's nothing at the third, nothing at the fifth, and nothing at the seventh harmonic. Around 4.4, which is the 11th harmonic in this case, with 400 meg fundamental, we do have 48 dB of noise, but that's still well below the 54, 10 dB, 6 dB below the FCC Class B limit. So it just goes to show that if you plan the PDN properly using the correct capacitors and you do it correctly from scratch, then your design will have less emissions. Thank you very much.